Hello, I'm Ed Wicklein with Corlo Engineers. I'm here today to talk more about the technical guidance manual on computational fluid dynamic modeling of chlorine contact basins we've been developing with the Colorado Department of Public Health and Environment. So we've put together a number of recorded modules. Hopefully you've had the opportunity to see Module 1, the CFD modeling overview, and look at Module 2, which is the review of the guidance document. Today, we're going to talk about an example problem. In the guidance document, Appendix B contains a sample problem and report that we worked through to help provide end users information on what should go into the report and how the department would like to see it organized. In the guidance document, we've got a CFD modeling process flowchart. And today we're going to talk about the first couple pieces that are going to go into our sample problem. So we do need to always define your objective. What are we trying to solve? Our objective is to determine the baffle factor of this representative tank. So some of the key assumptions in physics that go into our problem. It's going to be a double precision problem. So the computer has a number of decimal places to provide a high level of accuracy. We're going to use the simple scheme for velocity pressure coupling in our solution. It's going to be a second order accurate model. We want a high level of accuracy on our equation discretization. It's single phase with water only, with water being the primary fluid, as well as the tracer having the same properties as water. There's going to be a steady flow rate through the system, and the water level is constant. So given the steady flow rate and fixed water level, we are able to use a rigid lid approximation where the water level doesn't fluctuate and it is set as a wall with zero shear. We'll be using a capsulon realizable turbulence model to resolve the turbulent fluid motion. So our tank geometry is square, 50 feet by 50 feet. There's an 18-inch inlet and outlet. 18-inch diameter inlet and outlet pipe at opposite corners. It has a volume of 0.187 million gallons at the 10-foot operating depth. And there's internal baffling, creating a 9-pass serpentine path through the tank. Looking at research from AWWA-RF, we would estimate with a length to width ratio of 81 that the baffle factor is approximately 0.87 for this tank. We have a couple of operating conditions we're going to look at. The 90th percentile flow, a high flow rate of 4.5 mgd, giving us a hydraulic residence time of 60 minutes, and the 50th percentile flow of 2.5 mgd, which has a hydraulic residence time of 109 minutes. At this sample site, the water is 20 degrees Celsius all the time. So that gives us our density and viscosity that go into the problem. We do have some mixed units here. I typically use SI units in the CFD model. I find it tends to work better without having to convert between different units once you're within the model. But do pay attention to your units so that you're consistent and your conversions are accurate. And with that, you can send any questions you have, or we'll discuss them at the live session. Following this, we'll be moving on to developing the geometry of this tank within the computer model and developing the computational mesh. Thank you for your time today.